ما زال
Yeah,
بديتوا. اوكي. جست
we are
نتستيو
live.
معلش. جست نتستيو البرزنتيشن معلش.
Yeah, you can share. Okay. So, hello everyone, into our start of our School of AI Algiers event, the AI Summit, and we have high interesting talk starting our series of conferences, our online conferences before our on-site event. So the stage is yours, Mr. Riadh Baghdadi, and thank you very much. It's an honor to have you here with us as the kickstarting of our event.
Thanks a lot, Kamal. تحية ليك و I'm very happy to be here. Welcome everyone. So let me share my screen and then share screen. There's been a long time since I didn't use share entire screen. Share. Okay. You can see my screen. Let me know if you can see the presentation running.
Yeah, we can see it.
Sorry. Okay, perfect. Okay, great. So I'm very happy to be here, to be talking to members of School of AI, but also everyone joining from different places. So I know School of AI very well because first I like what you are doing a lot. I think there are a few clubs that focus on the technical, on very technical topics, and this is one of them. So I really like that, and also because I worked with a few members from School of AI before who did PFE Project 22 with me. Hajar Ben Mazian, the founder, I think one of the founders of School of AI, she did her PFA with me. Also, there are a lot of members afterwards who worked with me. Now this year, Nazim Bindib, he's working with us on things similar to what I'm presenting here. So I know you guys, I know that people from School of AI have very high quality. Very motivated to work on deep learning. So I'm Riadh Baghdadi. I am an assistant professor in New York University in Abu Dhabi, and in general, I work in the area of intersection between compilers and machine learning, the intersection between these two topics. And so one of the things that we work on is developing compilers for machine learning, basically things like PyTorch, TensorFlow, all of these frameworks. Behind the scene, they also have compilers to compile machine learning workloads. And so we work on projects similar to these. And we also use machine learning to improve compilers. And the presentation today is about the second type, where we use machine learning to improve compilers and make them optimize code automatically. And then we use this to accelerate machine learning code. So the talk is a deep learning based cost model for automatic code optimization. So the goal is to automatically optimize code in compilers. And then we use deep learning to build cost model to enable that. So the very long-term goal is to enable compilers to automatically optimize code. What do we mean by that? We mean we want people to write very high-level simple code, and then we use a compiler that automatically optimizes code to generate very efficient, fast code for the hardware target. This can be CPU, it can be GPU, it can be TPU. And so the developer doesn't have to care about the complexity of the hardware. They can just type simple code, and then the compiler automatically make it run very, very fast. And compute-intensive applications are everywhere, from deep learning to image processing, bioinformatics, scientific computing, and accelerating any one of these areas makes a huge impact. If we take a look at deep learning, for example, in the last couple of years, if you look at the years from the beginning of the deep learning revolution in 2011, 2012, to just 2019, just like a few years ago. And if you look at the amount of computing needed to train different models, that amount of computing needed has been increasing a lot. So for example, in 2012, when AlexNet, one of the early deep learning models that really showed that deep learning is really a very strong method, it required this amount of compute to be trained. But if you look at AlphaGo Zero required orders of magnitude, more than 300,000 more compute than AlexNet. And while AlexNet was trained on single GPU, AlphaGo Zero was trained on a cluster of GPUs. And if you look at today with GPT-4, GPT-4 just requires a tremendous amount of compute in order to be trained, right? And so the amount of compute is just increasing. It's becoming crazy. If we look at GPT-3, training GPT-3 required more than 4,000 GPUs that were running for months. And then the whole cost, if you do the training on the cloud, the whole cost would be more than $4 million. That's a huge cost to train just a single training. And as you guys know, in deep learning, sometimes we need to do a lot of experiments. We need to train a model and then train it again, and then we train it 100 times. And each time we change a parameter, we have a bug, we discover something. So you should multiply this $4 million by 1,000 or by 100 at least to really see the cost of developing GPT-3. So it's a huge cost. And if you look at an architecture like transformer neural network, that significantly big one that has 200 million parameters, training such transformer produces more carbon footprint than what car would produce in all of its lifetime. 5 times, actually, it produces 5 times more carbon footprint than compared to what a car would produce in all of its lifetime. So again, it's a huge carbon footprint. So training these the deep learning models requires a large computing resources. It's very time consuming, has very high cost, and has a high carbon footprint. And so there is a need to accelerate these models and make them train faster and run faster. And one of the ways to accelerate them, there are many, many ways. One of them is to do what we call code optimizations. And the term code optimization means applying code transformations to accelerate the model execution. That means changing the code so that the model runs faster. And of course, you can work on things like improving the model itself, designing a model that doesn't take a lot of time, or you can work on hardware accelerators, designing new hardware, like for example, designing TPU. So you can accelerate models in different ways. Code optimizations is one of them. And so let's take an example of code optimization. So if you look at the following TensorFlow code, this is a function that takes x, y, z as input and then performs the following computation. It adds x and then it multiplies y and z and adds x to it and then performs the reduction. If you run this code on TensorFlow, you get the following graph where first yz is multiplied, then the result is stored in an intermediate array, then you have x plus t, then the result is stored in an intermediate array, then you have a reduction, then you get the result. This is what you get by default in TensorFlow, but actually if you want to accelerate this code, you can apply an optimization called fusion that fuses all of these operations, this operation, and this operation, and this operation in the same kernel, in the same loop. And so you do all of these calculations at the same time in registers, and then you only produce one final result and put it in memory. What's the advantage of this optimization? The advantage is that you don't access the global memory a lot, you just use registers. And as you guys know, using registers is 100 times faster than, between 100 times and or even more than that, faster than using global memory. So you actually accelerate the execution of your code by a lot if you make your code just use registers. Now, you can do this optimization, but the problem is that you have to do it manually. So you have to spend a lot of effort You need to know to be an expert in code optimization, and you have to spend a lot of effort to actually implement this manually in TensorFlow. Or in PyTorch or in JAX or in any other framework. And if you apply this optimization, for example, you get about something in the range of 46% speed up, which is like you accelerate the execution by 2 times. So instead of the model training in 1 day, it trains in half a day, which is good. And again, as I said, these optimizations are done manually. In the general case, you might say, why is that? Why this is not implemented in library? The problem is that there is an infinite number of possible expressions, and we cannot implement every possible expression in library and optimize it. So there is no library that just performs this particular operation. And so if you want to do it in fused way, you have to implement it yourself manually, or you do it in this infused way, which is quite slow. And this problem is general because when you write machine learning code, especially if you are developing something new, doing research, usually you create new expressions that no one has ever wrote before. And so there is an infinite number of possible expressions, and we cannot write libraries for each one of these expressions. So we have to find a method to solve this problem. And so while some of these expressions, like for example, adding B and C, adding 2 vectors or 2 tensors, or 2 scalars, this is well implemented in libraries. But doing another operation like this, for example, you will not find that in library. So one solution to this is, or in our case, we are trying to solve this type of problems. So if you look at what Elon Musk tweeted some time ago, he actually, they are trying to solve the same problem. And so what he said, our neural network is initially written in Python for rapid iteration, and then it's converted to C++, C, and raw metal driver code for speed. And he says this is very important. So here he's talking about neural networks used in Tesla cars. So at Tesla, first there is a team that develops the model using PyTorch, Python, and the goal is to go fast, because when you use Python, you can develop very, very fast. And then when they design the model and figure out the right model, and they see that, okay, this works, then there is the second part of their work, which is taking that code and re-implementing that code in C++ or C, or even something lower level than C, to really optimize it and make it fit in real-time constraints. So because in driverless cars, you need a model that really runs very, very fast. The problem is that this manual task requires a lot of expertise, is very time-consuming, and is error-prone. So it's not ideal. And this is why we use compilers to do automatic code optimization. So our ideal goal is to enable users, ML experts, for example, to write simple model using the tools that they like, let's say JAX, PyTorch, TensorFlow, whatever the tool they like. And then behind the scene, there is a compiler that automatically optimizes that code and does all the necessary code transformations to generate super efficient code for different hardware targets, whether it's CPU, GPU, phone, distributed computer that has a lot of GPUs or CPUs or whatever. But automatic optimization is a very hard problem. Let me show you an example. If you take the following code, which is matrix multiplication, the original algorithm for matrix multiplication is super simple. But in order to optimize it, the compiler has to generate this very complex code. And in order to do that, it has to apply many complex code optimizations. It needs to check the correctness and composability of transformations. And the biggest challenge is selecting the right combination of these optimizations. Why is that hard? Because there are millions of possible optimizations that could be applied on the code. And then predicting the performance of each one of these optimizations is quite hard. There are complex interactions between these optimizations. So what do we mean when we say that the compiler has to select the right combination of optimizations in order to generate a code. What do we mean by that? So the problem of optimization selection in compiler means the following. So the compiler has a code as input, and it has a list of optimizations that it internally has. Like if you take the PyTorch compiler, if you take the GCC compiler, any compiler that you know and use, that compiler has a lot of optimizations internally. And when compiling code, the compiler has to select some optimizations and then apply them. So the problem of optimization is about finding which optimizations the compiler should apply on a given code given as input. And so as input, it will select, let's say, two optimizations, loop parallelization and loop tiling. We will not go into the details of what each one of these optimizations is, that doesn't matter. But the point here is that the compiler has a list of optimizations, and then it wants to select few of them to apply on the code, because applying these two will give you the best combination, or the best, it will minimize the execution time. It will give you the best performance. And selecting the right optimizations is crucial and important, because if you just add another optimization, it will make the code run very slow. And if you remove one of these, it will make the code run very slow. So really, to make it run very fast, you need to make the right selection, the right combination of optimizations, which are very, very hard to find. So if you think about the problem, let's try to model the problem. So let's assume we have, or the compiler has a code. It's a simple loop. Let's call it loop C. It's just a simple loop that has one or two statements inside. And then the compiler wants to explore whether it should apply an optimization called tiling. We don't need to get into the details of what tiling is. And then another enrolling also is another optimization called enrolling. So the compiler wants to know whether it should apply tiling, whether it should apply enrolling, or whether it should apply them together. These are just two optimizations that the compiler has. So one way for the compiler to solve this problem is to do the following. So the compiler takes the code, the initial code, and then it says, okay, should I apply tiling, the first optimization? And it has two choices. It can either apply tiling, or it doesn't apply tiling. So it has these two choices. So in order to decide between these two choices, it needs to use a cost model. The cost model would say, hey, if you apply tiling, you actually will accelerate the code by 2 times. Or if you don't, actually the code, or the cost model might say, oh, if you apply tiling, or maybe the code will run slow. Anyway, so it needs to use a cost model to decide about whether to apply tiling or not. Let's assume the cost model says, yes, you should apply tiling. And then it needs to choose the tiling parameters, basically these numbers. Again, we don't need to get into the details of what are the parameters and so on, but the compiler just has a bunch of parameters to choose from. Again, it needs to use a cost model to decide. Let's say it decides to use these. And then it will ask itself, now, should I apply enrolling? And the same thing happens again. And so as you see, the problem of selecting which optimizations to apply is equivalent to doing search in tree, search tree, and then using a cost model to guide that search, to basically figure out which combination of optimizations to apply. So we can decompose the problem of automatic code optimization or optimization selection into 2 subproblems. First, we do space exploration, search space exploration. We model the problem as search tree, and we search that tree. And then we need to evaluate each candidate in that space. And so to evaluate candidate, we need to do cost estimation, basically predict what's the speed up, how is the code going to be fast or not. And then we also need to check correctness. And so our work focuses on creating a cost estimation method, or basically cost model, using deep learning. So we use deep learning to build a model that predicts whether given optimization is gonna accelerate code or not. And then for search space exploration, we use classical techniques like beam search. These are techniques for searching tree, Monte Carlo tree search. The technique itself doesn't matter, but these are just classical search techniques that we use in exploring in tree search. So our goal is to build a deep learning model for speed up prediction. This model takes a code and list of code optimizations, and then it uses deep learning to predict what's the speed up that you would get if these optimizations were to be applied on the code. And so the speed up is just, if the speed up is a number, if it's higher than 1, that means the code is going to run fast. If it's below 1, it means the code is going to be to become slower compared to the original code. So it's just an indicator about whether these optimizations are good or not. And so let's get into directly, I will not talk about tiramisu, but let's talk directly about the cost model itself. So tiramisu is the compiler on which we implement all of our work. So all of this work we have implemented this in tiramisu, and now we are doing the same thing also in the MLIR compiler. So MLIR is a compiler that is developed by Google and used to compile JAX, to compile TensorFlow, and also to compile PyTorch. And this is what Nazim Bendib is working on. He's using reinforcement learning with deep learning to automatically optimize code in the MLIR compiler, and basically getting inspired from all of this work to solve that problem. So let's talk a little bit about the deep learning based cost model that predicts speed up. So again, it's a model, deep learning model, that takes code as input and list of code optimizations and predicts the speed up. So let's start by looking at what's the representation of the input. Basically, how do we represent the code and the code optimizations, which are the inputs to the model. So let's assume we have the following code, which has few loops for I, for j, for k, and we have statement, computation A. This is just statement A. Then we have another loop, and then we have statement, and then here we have a bunch of statements. So we represent this as a tree, where we have here the loops. This is the loop I, it's here, the loop j is here, and then within the loop j we have the loop k, lm, so we have k, lm here. So we present this code as tree. We call this an abstract syntax tree. It's tree representation of the code. And then each one of these statements were represented as a vector. And this vector has just a bunch of features that represent the statement. For example, we have features that represent how memory is being accessed, what are the operations that are done, how many additions, how many multiplications, things like that. We also have features that represent the size of each loop, what's the loop extent, basically how many iterations in this loop, and things like that. And then now this is the input representation. Now this is what the model looks like. So also, since the input is represented as tree, so the model is also follows that structure. So in our model, we have 3 parts. The first part, we have feed-forward neural network that takes that vector that represents the statement and creates an embedding. And we do this for all the statements. So we get these embeddings, green embeddings that represent the statements. And then we have this yellow part, which is an LSTM that combines different embeddings of statements and creates a new embedding that represents the loop. So each loop we process that using an LSTM. And so you get this embedding that represents the whole loop. And then we keep doing this in a hierarchical way until we reach the final embedding that represents the whole code. So for example, these embeddings, this is an embedding that represents the K loop. This is an embedding that represents the L loop. This is an embedding that represents the M loop. We put all of these in an LSTM, and then we create an embedding that represents the J loop, and so on. And then here we have feed-forward model that takes this embedding and predicts the speed up. The next question is, now that we have represented the input, we have a model, we need data. So the question is, how can we get data? We don't have millions and millions of data points of tiramisu, of code optimized in tiramisu. So how do we solve that? We solve it by generating random programs and optimizations and run them. So we don't have data, so we generate and create this data. How do we create it? We generate random programs, and for each randomly generated code, we generate random optimizations, and then we take the code, we compile it, and then we run it, and then we get the final speed up. And so the data points that we get are the original code or the algorithm, and then which is generated randomly, and then a bunch of optimizations also generated randomly, and then the speed up that you would get that we got when we actually compiled the code and ran it and executed it. And so the code generation is guaranteed by construction through our code generator. And in this work, we had 1.8 million data points that were generated using a cluster of nodes. It took the data generation took about 3 weeks. So let's look at an evaluation. This is a graph that shows the comparison between predicted speedups and measured speedups for a bunch of randomly generated programs. So we take a subset of the test set, and then we plot it like this, where the red dot, basically this red line, is the measured speedup, the actual speedup of the code, optimized code. And then the blue dot, these blue dots are the speedups predicted by our model. And ideally, the speedup predicted by the model should be close to the measured speedup. And as you see, that's actually the case. For all the programs, the speedup that we predict, let's say we take this point here is close to the red point. So it's quite close. And so as you see it for different, and then we just sort them to make the visualization easy so that it appears like this. Here we have a little bit less accuracy, but I mean, it's okay. It doesn't hurt a lot. In general, there is a big correlation. And in general, the mean absolute percentage error is about 16%. And so this is kind of zoom on the speedup, the error distribution across speedups. So for different speedups, as you see, we have different error percentages. So for speedup close to 1, we have a very high or very low error, but for other speedups, we have different errors. I will not get into the details of the slide, so I'll just move on. So the question now is this cost model actually effective in optimizing code? So let's try it on a real use case. So here in this graph, we evaluate our automatic code optimization that uses this cost model on a bunch of programs, real-world programs. So this is an image processing application called Box Blur, which just makes an image blur. This is convolution plus ReLU from deep learning. This is convolution. This is color conversion. These are a bunch of applications. And then here we show speedups over a baseline. And so the goal now is to use our automatic code optimization, which uses beam search. But instead of using the cost model, we use execution. We actually take the code and compile it and run it and measure the actual speedup. And use that to optimize the code. So this is equivalent of using a perfect model, because now we are doing the search using search method, but instead of using our cost model, deep learning based cost model, we are actually getting the ground truth. We are compiling and executing the code. So this is the ideal speedup. Let's compare our method to the ideal speedup. So the green bar is our method compared to the ideal. Our method, we use beam search to explore the space, and then we use cost model to do the estimation. And ideally, the green bars should match the blue bars. So here in Box Blur, we match the blue bar. Here in conv-ReLU, we match the blue bar. So for example, if you use beam search plus execution, you get a speed up around 2. Basically, you accelerate the code by 2 times. But also, if you use our method that uses deep learning cost model, you also get the same. And in almost all of them, it's the same, except in some of them, in Seidel2D, for example, there is some difference, but it's not a huge difference. And then the other things are just MCTS. We are using Monte Carlo tree search instead of beam search. And then here we are using Halide to automatically optimize code. As you see, the code that we optimize is much faster than the Halide optimized code. Okay, so I will stop here. In general, let me give a summary. So what I presented is a deep learning based cost model for automatic code optimization. And the main features is that this deep learning model does not require heavy features, and it's designed to predict speed up. And this project is available as an open source project. If you go to the Tiramisu website, this website here, you can find the Tiramisu compiler, and you can find the code for this automatic code optimization and for the model, and just play with it. If you want to, let's say, take this model and improve it to maybe make it more accurate, that would be research, very good research contribution that you can publish about. So if that's something interesting to you, let me know. Before we stop, so this was my last slide. Let me just get back to here. So before we stop, let me keep the slide sharing. So before we stop, also I wanted to say that if you are interested in doing any research around this, please let me know. We are very happy to work with you. We always get students that do summer internships with us during summer. So last summer we got few students. Unfortunately, we cannot work with a lot just because we have limit in number. But at least we work with few. Also, we have PF projects, Project Finitude, for those of you applying for next year, inshallah. So these projects are around using reinforcement learning to do automatic code optimization, but now we are focusing more on the MLIR compiler. So MLIR is a compiler, as I said, developed by Google that is currently used to compile TensorFlow, PyTorch. So in this project, we have collaboration with two teams, with team from MIT. So we are building a compiler for physics team from MIT. And so we are also doing automatic code optimization for them. And we are using reinforcement learning for that. And then also we have collaboration with MathWorks. These are the people who built MATLAB. So we are using MLIR and our automatic code optimization to automatically optimize MATLAB code. And so we are using reinforcement learning for that. And then there are also new projects related to using deep learning to directly predict optimizations rather than using these methods. There are other methods, other projects about using large language models to do these automatic code optimization. And then there are different methods about, in general, making machine learnings run faster using things like neural architecture search or quantization or those other techniques. Okay, so I will stop here and I will be happy to answer your questions if you have any questions.
So thank you very much, Mr. Riadh Baghdadi, for your very interesting talk. And we already can sense its impact on the deep learning realm and artificial intelligence revolution right now, especially by enabling to have like faster code and enable to have more impactful projects that can revolutionize the evolution of AI. So for the questions of our attendees, so we do have a question from Yunus Khadrawi about what is a TPU. So we did
Yes.
have like answer from Ramses saying that it stands for Tensor Processing Unit. It's just a hardware device that is delegated to perform computations on matrices efficiently. For example, doing a matrix by matrix in a single instruction. So if you would also elaborate more on question.
Yeah. Yes. So TPU is very specialized accelerator that accelerates these tensor or matrix operations, exactly like Ramzi said. And it's very, very fast. If you do matrix operations on CPU, they are very slow. If you train a model on CPU, it's very, very slow. If you train it on GPU, it's much faster. TPUs are the Google version of those GPUs. They're an accelerator of deep learning training. Yes. So they asked for the email. Please, how can I write it? Join chat. Okay, I cannot write it here, but let me. So if you go to my website, just type Riadh Baghdadi. You can find the email, or I will type it to you, Kamal, and then you can just paste it if you want.
All right.
Okay, I'll put it in the private chat. So you can post this if you can.
All right. So there is another question from Nasima Usahbo saying, do you only supervise at the AI school? Maybe she would mention, she meant maybe School of AI. Or...
Yeah. In general, I'm very happy to talk. So just send me an email, send CV. and we can talk, inshallah.
Okay. So another question from Yunus Khadraoui saying, can you use LLMs for code optimizations?
Yes. So we have colleagues working at Facebook, Hugh Leather. He actually collaborates with us a lot on supervising students from Lizzie, and they work a lot on using LLMs. I mean, lot in the last couple of months they work on using LLMs for code optimizations. They have shown that they took Llama 2 and they fine-tuned it to code optimization, and they showed that it works really, really well. So we are very interested in exploring this area.
Right. Another question from Ramzi saying, are the code optimizations made by deep learning cost model microarchitecture dependent?
Yes. In the work that I presented, yes, they only work for specific architecture. So if you want to make them work on another architecture, you have to generate the data again for the new architecture, and we still don't have a method that works for all of them. I mean, that's a research question that we're interested in exploring.
All right. So that's a thanking question from Bushusha Mohammed Amin saying, thank you for sharing such valuable ilm with us. Happy to have you with us.
Thanks a lot.
Right. Another question from Sami saying, how to define the acceptable success rate for this project?
Yes. So the way we work is we have in a research project, you just need to be better than existing work. So you take existing methods and you show that you are better than them. That's all what you need. You don't need, like when we say the error is 16%, I mean, for some areas it's too much, for some areas it's not. So you just need to look at what's the best existing work, the best research, the best work done in companies, and you just need to be better than them. And then whoever comes after you has to be better than you, and that's it. That's enough.
All right, that seems that's all we have. So again, thank you very much, Mr. Riadh Baghdadi, for your time and for your interesting talk and insights you gave us all within our event Summit. We can say that we have started our event very successfully, having such an amazing talk with us. So, and for all our participants and attendees out there, stay tuned for more interesting talks with us in the AI Summit. And thank you again, Mr. Baghdadi. And thank you all for your attention and attendance.
Thanks a lot. Thanks a lot, Kamal. Thanks to all of you guys at the School of AI. I really wish you continue this very nice work. So this is very good. So keep up the very nice work. And for all of us following us, deep learning is very, very interesting area. It's really booming now. So I highly encourage you to really get into this field and work in this field. It's very, very interesting. So thanks a lot. Mohammed is here. Hi, Mohammed. Okay, good to see you all, guys.
Thank you very much, everyone.
Thank you.